Hello everyone, welcome to Chapter 3 Derivatives, and here the focus is on derivatives of trigonometric functions. I know you look forward to trigonometry. Okay, so here again we have a set of rules that you can use to quickly differentiate or find the derivatives of trigonometric functions. I'm going to put that up first, and then I'll do a couple of derivatives to show how it was derived. Okay. So here is the list of all the derivatives. So derivative of sine x is cosine x, derivative of cosine x is negative sine x. For tan x it's secant squared x, derivative of cosecant x is negative cosecant x cot x. Looks a little different, but you can remember it as c and c, cosecant and cot, which c functions. Derivative of secant x is secant x tan x, and derivative of cotangent x is negative cosecant squared x. Now these are all obviously derived from the traditional limit dq idea of derivatives, and because it's trigonometry, it also involves trigonometric the identities that we use there. And so let's do a couple of derivatives. Okay? Let's derive cosine x. So we need two functions, right? You need the f of x, which is we're going to call as the cosine x. But we need the x plus h. So that will be cosine, and in the place of x, it will be x plus h. Again, please do not add the h in the end. It is added to the x, wherever x is. So replace your x by x plus h. And here we use the trig identity, which says, it's basically the sum rule, it's called, sum identity. So cosine of x plus h is cosine x cosine h minus sine x sine h. Okay, and we are trying to find the derivative of cosine x. So derivative of cosine x will be f prime, because f is cosine x, so f prime of x is limit as h approaches 0, f of x plus h minus f of x all over h. Right? That's the traditional definition for the derivative. And here f of x plus h is cosine x plus h minus cosine x over h. And we just found the expansion for x plus h, cosine x plus h, to be the identity. So that's going to be cosine x cosine h minus sine x sine h minus cosine x all over h. What I plan to do now is collect all the cosines together and separate it from the sine x. Center it now. Cosine x. So I'm looking at only the cosines, okay? So cosine x is common. So I have cosine h minus 1 minus sine x sine h. Right? That's what you have in the numerator. All over h in the denominator. So we must always understand this whole thing is we apply the limit for the whole thing. So here too, I want to apply the limit for the whole thing, but I want to separate the cosine and the sine. So because they have the same denominator, I can separate them into two fractions, right? Each carrying its own h. That means I can now separate the limits by the sum rule. And there is a reason why we do this. You'll see that shortly. This some more. All right. Now if you look at the limit is applied as h approaches 0. So the play here is all about h. So if you look at the cosine with the x and the sine with the x, anything that has the x is kind of treated like a constant. Therefore, we're going to pull out the cosine x from the first term and apply the limit only where it matters, which is cosine h minus 1 over h. And here I'm going to pull out the sine x and apply the limit to sine h over h. And we've seen the rules before, that this part here, this whole thing, this thing is equal to 0, right? This is coming from the time we discussed about the squeeze theorem. And this one, we know that it's equal to 1. And so if you just applied that, you get cosine x times 0 minus sine x times 1. So this simply gives us negative sine x. Thus, we have proved that of f, which is basically the derivative of cosine x, comes out to be negative sine x. Thus proved. Now let's solve for, or let's prove for tan x. So we're trying to find or show the proof for derivative of tan x, which we are told is, or at least from the rules, is secant squared x. Let's go about proving this, okay? So the derivative of tan x can be written as derivative of sine x over cosine x. And that immediately allows us to see this derivative as quotient rule, where sine x could be u and cosine x would be v. Okay. And this derivative is done under the assumption that we have found derivatives of sine x and cosine x already. So I'm going to use that information to continue on here. So the quotient rule says derivative, maybe I'll just write it in, u prime v minus v prime u over v squared, right? That's the derivative formula for quotient rule. So keeping that in mind, u prime times v, which is cosine x, minus v prime, which is derivative of cosine x, times u, which is sine x, all over v squared, which is cosine x, that is to be squared. So we saw that derivative of sine x is actually cosine x. That times the existing cosine x, minus derivative of cosine x is negative sine x. Remember, there is a negative in the setup, in the rule, and there is a negative that comes from the derivative. So there will be two negatives. And cosine x, the whole squared, is the same as cosine squared x. So what I have here is cosine x times cosine x, which is cosine squared x. And minus will become plus sine squared x over cosine squared x. Again, from trigonometry, cosine squared x plus sine squared x is equal to 1. So 1 over cosine squared x. And that's nothing but secant squared x. You see, thus proved. And so that's how we arrive at these rules, these derivatives for trig functions. So I showed 2 of them for you as sample. I hope you're curious enough to go and verify the others. So now I'm going to move on to some examples. Find dy over dx where y is x squared minus sine x. as always, write out what you are asked to find, and then you replace your y by x squared minus sine x. Then take the derivatives individually. Derivative of x squared is 2x minus derivative of sine x is cosine x. So that's it. We found it right away to be this. That's the derivative. Here's our next question. What about x squared times sine x? Ooh, that's different. Not as easy as what we saw in the previous example. Nevertheless, write it out. Now clearly there is no plus or minus in between them, so you know that they are being multiplied. So I'm going to call x squared as u, and sine x will be my v, so that the product rule will kick in. U prime v plus v prime u. Okay, that's the product rule. Derivative of products. And therefore, for the first term, u prime, derivative of x squared is 2x times, maybe I'll just write out the steps in expanded form just for clarity. U prime v plus v prime, so derivative of sine x times u. That's going to be 2x times sine x plus derivative of sine x is cosine x. It's cosine x times x squared. Let's come down here and clean them up. So it's 2x sine x plus x squared cosine x. We always like to put the variable in the front and then the trig function. And that's the answer for that. So remember to understand and apply the correct rule. Here's our next problem. Y is sine x over x. And in the place of y, I have sine x over x. Once again, make the connection that you now have the top as a u and the bottom as a v. U prime v minus v prime u over v squared is the quotient rule. So derivative of u is cosine x. I'm slowly getting away from showing every step explicitly. So u prime v is what I have here already, minus v prime, which is 1, times, write that 1 again clearly, times sine x, all over x squared. So that's basically x cosine x minus sine x over x squared. And that's the answer there. Because I'm trying to drive home the idea here and how to use derivatives of trig functions, I'm just sticking to the y and the x. Okay? But again, remember to be open to other variables. All right, I see the plus in between the two terms, so we know that we can, individually find the derivative. So derivative of 5x is 5 times 1, plus derivative of cosine x is negative sine x. That's going to be 5 minus sine x. That's the answer there. Y is, in the next problem, sine x times cosine x. You don't see a plus or a minus, you know that this has to be treated as a product rule. And so u prime v plus v prime u will be our product rule. So derivative of sine x is cosine x times cosine x, plus derivative of cosine x is negative sine x times sine x. That's going to be cosine squared x minus sine squared x. Unfortunately, we can't reduce this. If we had a plus, then that would reduce to a 1. But here, you could use a double angle and things like that, but that's not considered as simplified. You should just have the x. You can't have 2x as your angle usually in the simplified form. So we leave the answer like this. Y is cosine x over 1 minus sine x. Okay. Okay, you know the drill now. The numerator will be u, denominator will be v. So we want to be super careful here. So I always like to write the formula for that corresponding rule. U prime is negative sine x. V is 1 minus sine x. U prime v minus v prime. You have to be super careful here. V prime is 0 minus cosine x times u all over v squared is 1 minus sine x. This whole thing has to be squared. Again, watch your algebra. You shouldn't be squaring them individually because you'll be losing a term if you did so. You're squaring the entire v. So put the square outside, put the parentheses for the denominator and square it. Let's see what we have here. So cleaning this up gives us, so there's a minus, so that will be plus cosine squared x all over 1 minus sine x, the whole squared. And we know we have some good news here, because this we know is equal to 1. So I can put the 1 in the front. I say 1 minus sine x over 1 minus sine x, the whole squared. We could have expanded the denominator. It's usually a good idea to see if something can cancel off, if you could find matching factors up and down. We do find matching factors up and down, so out of the square, one of them will be cancelled off, and that leaves us with 1 over 1 minus sine x. That is the answer. Now, what happens if you're asked to find the limit, say, limit of x approaching 0 for square root of 2 plus secant x all over cosine of pi minus tan x, something as complicated as looking as this. Now we know that differentiability implies continuity, right? Let's just quickly write that information here. And we saw that in terms of trig functions, they are differentiable in their natural domains. So because of that condition there, we can definitely apply the limit by direct substitution. Why? Because we are sure that if there is continuity, then the function value and the limit value will match. Remember those 3 conditions for continuity? So we're going to call upon that because of this robust, protection we get because of this underlying rule that differentiability implies continuity, and for the fact that trig functions are differentiable in their natural domains, and therefore they are continuous in their natural domains. All right, so then in this case, let me write this one more time. I can directly substitute for x as 0, so that will be 2 plus secant 0 all over cosine pi minus tan 0. So you want to go back and look at your unit circle. Secant 0, so we don't see the unit circle directly as a secant value, but you can find the cosine value. So cosine 0 is 1, reciprocal of cosine is secant. So reciprocal of 1 is 1 again, 2 plus 1, over cosine pi minus tan 0. Tan 0 is sine 0 over cosine 0. So sine 0 over cosine 0 will be 0, right? Because sine 0 is 0 and cosine 0 is 1. So 0 over 1 is 0. So we get that as 0. On the top I have root 3, right? 2 plus 1, 3. Over cosine pi, because pi minus 0 is pi. Cosine pi is negative 1. So I have root 3 over negative 1, which is negative root 3. So by direct substitution, we were able to find this value for this expression. Always we need to be careful that we never lead ourselves to direct substitution where it's algebraically undefined, meaning if your denominator becomes 0 by direct substitution, then you'll have to go into other algebraic techniques or other trigonometric techniques like using identities to overcome that hurdle. Now let's try to connect this information that we have with the equation of a tangent line, because we've always seen them for polynomial expressions, but let's see it for a function that is a trigonometric function. Okay. Find the equation of the tangent line to the graph at x equals pi over 2. So remember, we're trying to find the equation of the tangent line for this trig function at that point pi over 2. So this is equation of a tangent line, so we need the slope and the point for the slope point form. So to find the slope, we need to find the derivative, right? And we find the derivative at x equals pi over 2. Remember that notation? And for the point, we already have the pi over 2. Plug that in the f function, and that gives you the slope and the point. Then put that in that slope point form, and you got your answer. So this is our plan. So let's go ahead and start with the slope. So I first write f of x as negative 3 cosine x, and f prime of x will be negative 3, and cosine x is, derivative of cosine x is negative sine x, which is going to be 3 sine x. And we need to find the slope at this point, f prime of x at x equals pi over 2. But the crisper notation for this would have been simply f prime of pi over 2, because in the place of x you now have pi over 2. But I want to expose the two ways we can write that. And so f prime of pi over 2 will be 3 times sine of pi over 2. Sine pi over 2, sine 90 degrees, that's going to be 1, which is 3 times 1, 3. So we found the slope. Now we need to find the point. F of pi over 2 would be negative 3 cosine of pi over 2. And f of pi over, cosine of pi over 2 is cosine 90 degrees, which is 0. Therefore, that's going to be 0. So let me collect all the details I have. Slope is 3, and the point is x comma y. So pi over 2 comma 0. So now I have to use the slope point form, which is y minus y1 equals m times x minus x1, because this is going to give me the equation of the tangent line, and y minus 0 equals m, which is 3 times x minus pi over 2. So technically that's y equals 3x minus 3 pi over 2. That is the equation of the tangent line. Sometimes they can ask for the derivative at a point, but just that this is going to come as a trigonometric function. So it's the same stuff, we're just seeing it in terms of trig. So if I had a question that said find the derivative of f of x equals negative cosine x plus sine x at the point x equals negative pi over 2. Well, of course, we find f prime of x, which is negative of cosine, derivative of cosine is negative sine x, plus derivative of sine x is cosine x, which is the same as sine x plus cosine x. And f prime of x at the given point x equals negative pi over 2 is the same as evaluating f prime at negative pi over 2. Therefore, you plug in the place of x negative pi over 2. We don't usually see negative angles, but that shouldn't be a problem. Calling back on the idea of oddness and evenness of functions, you know that sine function is an odd function. That means it spits out the minus. The minus goes in front of the function. Cosine function is an even function. That means it absorbs that minus. So what you'll see then is that the minus comes out for sine pi over 2, and the cosine absorbs that minus, so it's the same as saying cosine of pi over 2. So sine 90 degrees is a 1. With a negative, it's negative times 1. Cosine 90 degrees is 0, so the answer is negative 1. The derivative of that given function at the point x equals negative pi over 2 is negative 1. So with that class, we are done with this section. It's thankfully a very short one for us, and I will see you in the next part of chapter 3.